Question 4. The photograph shows a person on a ladder which is propped up against the wall at an angle theta to the horizontal. You've got the ladder and a person from a system. Diagram shows four forces acting on the system. Friction between the wall and the ladder can be neglected. One of the forces has been labeled. Okay, so here we have frictional force, which is opposed by the reaction force from the wall, and we've got a reaction force from the ground onto the ladder, which is opposed by the weight of the ladder and the person together. So this here is the force of the wall on the ladder, the reaction or the normal contact force from the wall, and here is the force on the ladder from the floor, and it's a normal contact force from the floor, and this here is the weight acting downwards. Okay, now complete the diagram by labeling the other three forces acting on the system, which we have here. That's 1 mark for these two and 1 mark for that. Part B, use the principle of moments to explain why the system is stable in the position shown, but will topple over if theta becomes too large. So what we do to answer this 6-mark question is split this into two. First, we're going to explain why the system is stable in the position shown, but then we are going to look at the second half of this question by looking at when theta becomes too large. Okay, so to begin with, we can see from this, if we identify a pivot point, that is the base toppling over, generally the ladder is going to pivot around the flow. So therefore, it is ideal to choose this as your pivot point to discuss this particular question. Now, if we use this pivot as our pivot point, this and this don't come into the principle of moments because they're sitting on the pivot and have no distance. So therefore, the only force that we need to consider, one is the anti-clockwise moment created by the weight. Okay, so that component is what we need to consider, and the clockwise moment created by the force of the wall on the ladder, the reaction force creating a clockwise moment. Now, we don't need to do any calculations, but we do need to discuss it. Okay, so what does it says? Use the principle of moments. So if that's the first thing to write down. What is the principle of moments? Okay, the system is stable, and the idea of stable is because the object's in equilibrium. So that means that the anti-clockwise moment from the weight is equal to the clockwise moment due to the reaction force of the wall. Okay, so this is something that you need to say specifically, not just as a general, the sum of the anti-clockwise moments are equal to the clockwise moments. Which moment created by what? Okay, so that picks you up the additional mark. This is when the moments are taken with a pivot point located at the base of the ladder. Okay, so what you need to do is identify where you are taking the moments from, not just saying clockwise moment equals anti-clockwise moment. So here we needed to talk about what is meant by this idea of stability. We are talking about the principle of moments, but we have included what is causing the clockwise and anti-clockwise moments respectively, and we are identifying where the pivot is. In a calculation, you will have numbers to verify all of this. However, we are writing it all in words. So this will give you 1 mark, this sentence here, identifying the pivot point, identifying the clockwise equals the anti-clockwise, and identifying which forces are creating these two will pick you up the second 2 marks. So that there is your 3 marks. And then the next one, you are looking at when the angle becomes too large, okay, to cause the object to topple over. So let's have a look. What happens is this angle gets larger and larger and larger. So that means that this ladder is becoming more and more vertical. Okay, so that means that there is less a frictional force acting against to stop to cause the ladder to slide, and that means there's less reaction force from the wall. Okay, so just imagine a position where the angle is 90 degrees. So the angle is perfect, the ladder is perfectly vertical like that. So that means it's not really, the wall is no longer pushing on it. So therefore there's no reaction force. So also, what you notice is that the weight is now on the opposite side of the ladder. It's no longer on this side of the ladder, created a anti-clockwise moment, the weight. But when the angle is 90 degrees, we see the weight shift to the other side of the pivot, and that creates this clockwise moment. And there is only one moment here. Okay, there's no reaction force from the wall, so there's only one clockwise moment, and that's your perpendicular distance to the pivot, to that force. And then as a result, what's going to happen is this ladder is going to topple over. So how do we write all this out? So when theta becomes large, the reaction force from the wall and the ladder decreases. Eventually at 90 degrees, the ladder is vertical and there is no reaction force, hence no clockwise moment from the wall. Okay, then where we could talk about the angle 90 degrees, now the weight of the person is shifted to the other side of the ladder, as we can see, is now pointing on the right hand side of the pivot compared to this here, which is on the left hand side of the pivot. And to the other side of the ladder, creating a clockwise moment. There's no anti-clockwise moment to counter it, to maintain equilibrium. Therefore, the ladder topples over. So that there is a complete answer for stability of that particular ladder.